So good afternoon, and we are on the fourth day, I believe. Hope you are enjoying the lectures. Yesterday we have discussed on thermal remote sensing, and particularly what are the advances in thermal remote sensing in terms of the data availability, these thermal missions, satellite missions, and the thermal sensors, then data processing, and different kind of applications. Okay, and also we have started this year microwave remote sensing, and what are the recent advancement in microwave remote sensing for geological applications. Okay, now we are continuing with that. Okay, so we have already discussed that there are a number of advantages with radar remote sensing, radar microwave So there are certain unique properties. We have discussed that it has a side-looking geometry, so it is very sensitive to surface geometry, and therefore it is very useful for geomorphological your feature identification and geological structures. Similarly, because it is a coherent radar, okay, so it is very sensitive to surface roughness, which is very useful for lithological discrimination. Then it is sensitive to moisture content, dielectric property of the material. So that is very useful for different kind of geological materials, like those are different in terms of dielectric properties, like unconsolidated materials like alluvium, like your hydrated mineral deposits, like your altered minerals like gosans. Okay, so those kind of features you can identify better in case of radar microwave. And most importantly, it has this penetration capability. It can penetrate through vegetation, and it can penetrate through ground. So that is why you can get some of the subsurface geological features like buried paleochannels, like active faults in alluvial terrain. Similarly, you can get the image of the terrain in a forested area. Those things we discussed yesterday, isn't it? And also we discussed that there are different bands available in microwave radar, and what are the missions at this moment providing us data. That also we discussed a bit, isn't it? So now, for example, at this moment we have data from RISAT 1A, that is from ISRO mission, okay, ISRO satellite. Then we have data from Sentinel-1, and then we have data from ALOS-2. Those are at this moment, these satellites are orbiting. Okay, then RadarSat-2, then we have this Cosmos SkyMed, then we have SAOCOM. So number of other these satellites are there, and there are certain satellites or certain missions are going to be launched in the very near future, like ISRO, which will have two bands. One is S band and L band. So it is a dual frequency, and it have lot of these good applications you can do, because its imaging mode is very special. Its imaging mode is a sweep-star imaging mode. It can cover a very large area without compromising the spatial resolution. And the data is also very your good quality data you will get, which can be used for polarimetric SAR, which can be used for interferometric SAR. So you will get this land surface deformation, very precise measurements you can make, and this different kind of ecosystem, then cryospheric applications. Okay, then soil moisture mapping. So there are plenty of applications you can do with NISR, which is scheduled to be launched in the next year, January, February, something like this. And there are other future missions like your Tandem L, that is L-band radar, then Biomass by European Space Agency, that is this very unique mission with the P-band. Okay, P-band is very long wavelength, 70 centimeter wavelength. In a satellite, we will have a P-band data. Okay, so now moving forward, so in case of this electromagnetic radiation, electromagnetic radiation is the combination or is the resultant of electrical and magnetic fields, isn't it? So electrical field and magnetic field combined together, we get your electromagnetic radiation, and this propagates, as you see this arrow, it propagates perpendicular to the electrical field and the magnetic field. Electrical field and magnetic field, they lie in a plane. Okay, this is also known as the electromagnetic plane, and perpendicular to this plane, this electromagnetic radiation or the radar pulse that propagates. Okay. Now in this slide, what is my interest is to introduce you what is these unique properties of this polarization behavior of the electromagnetic radiation, and from which you can have some measurements from the polarization behavior of the electromagnetic wave. So that is why it is also known as polarimetric SAR, means polarization plus metry. So some measurements from the polarization behavior of the electromagnetic radiation. Okay. Now you see this polarization behavior in radar backscatter wave from a feature, it is governed by some geophysical properties. This, for example, dielectric property, surface roughness of the feature. Okay. Also it is governed by the geometry and structural complexity of the feature, like shape, size and orientation of the feature. Okay. So you will have this kind of very special information from remote sensing data. So that is, you will get from where? You will get from polarimetric SAR. Now see, in case of polarimetric SAR, it represents the full this vector nature of the polarized electromagnetic wave. Why? Because it has the amplitude of the electromagnetic radiation, it has the phase information as well as the polarization this information of the wave. So all these three information you have together, and it gives the complete this information about the electromagnetic wave. Now you see this polarization can be of different types. It can be this your elliptical, that is the generalized nature of the polarization. It can be circular when there are the two orthogonal electrical vector, okay, this perpendicular to each other, and it can be linear. Linear means when the electrical vector remains constant. It does not change its orientation, it does not change its magnitude, then it is a linear polarization. So we are not going to the details about the polarization because it will not permit within this the scope of this your very short and special course. So here we will only discuss about the linear polarization. However, we will discuss about what is polarimetric SAR very briefly, and what are the your advancement in polarimetric SAR, and what are the some of the these advantages of polarimetric SAR at the later part of my lecture. Now at this moment, what we are discussing is the linear polarization. See, in case of linear polarization, electrical vector remains constant in terms of orientation. Okay, like this, it vibrates like this, and its magnitude is always constant. Now, when this electrical vector is oriented vertically like this, okay, then it is known as vertically polarized. This your radar wave. Now, this from this antenna, where is your this radar pulse is transmitted, then you are transmitting this vertically polarized wave. Now it is traveling and it finally it is interacting this with the earth surface, isn't it? Now after interacting with the earth surface, this orientation of the electrical vector can change. Okay, it can change to anything depending on the geometry, depending on the dielectric property of the material. Then it comes back to the antenna. Some part, not this entire part, the some part, it depends again on the geometry of the surface, it depends on the surface roughness. So this radar pulse, after scattering on the earth surface, it is coming back. So it is known as backscattered radiation or backscattered wave. So when it comes back to the antenna here with which is there in the satellite, there is the receiving antenna, okay, then this electrical vector can have different orientation, but you are receiving only the vertical polarized wave. Then this what return signal you are receiving, it is known as VV, because you are sending vertically polarized wave, then after interaction it is changing to many. Now, but you are only receiving the vertical. So vertical transmitting, vertical receiving. Similarly, if you are sending this horizontally this vibrating wave, that means the electrical vector is horizontal in orientation. Okay, if you send this radar pulse like this, where the electrical vector is horizontal, now after interaction it is coming back, it is changing its orientation into different in many, but you are receiving only the horizontal this polarized wave. Then it becomes this HH polarized this radar image. Okay, one is VV polarized radar image, another is HH polarized radar image. They are known as co-polarized because whatever polarization you are sending, you are receiving the same. This is known as co-polarized or like polarized. Okay, same polarization you are sending and receiving. The others are known as VH and HV. They are known as cross-polarized radar image because you are sending V but receiving H. You are sending H but receiving V. Okay? Just the opposite. So now you see, because of this different polarization of the radar wave, okay, their interaction with the Earth surface also will be different. Okay, for example, if there is HH and VVs in this radar wave are this interacting with the Earth surface, then what will happen? How much will be the this radar wave scattered back to the antenna? So if the surface, it depends on the nature of the surface. If the surface is rough in terms of the wavelength of the radar, so if the surface is rough in terms of the wavelength of the radar, then we can call that this here the scatterer, that means elementary targets where the scattering takes place, they behave like Bragg scatterers. So for such surface, what will happen? For such surface, your VV backscattered this signal, that means the VV backscatter image intensity will be greater than the HH backscatter image. So this VV image will look brighter than the HH image. But if the surface is smooth like this, and there are features, those are dihedral in nature, there is like this feature, one is face like this, another is perpendicular to this, okay, then what will happen? This transmitting wave will interact, then it will reflect, then again it will reflect here on the stem of the tree and it will come back. Here just example, it is tree or it is this surface, but it can be anything. It can be a bridge, okay, it can be any kind of buildings, okay, where you have one ground surface and one building wall, for example. So dihedral surface, for example, if it these features like this, then what is going to happen? So here you see this surface is smooth, that means here the scatterers are Fresnel scatterers, okay. These scatterers are known as the Fresnel scatterers, or they are defined as the Fresnel scatterer because their surface roughness is very, very low. So in terms of the wavelength, almost there is no surface roughness. It is smooth absolutely. So then it is known as the Fresnel scatterer. Okay? There will be dominantly reflection and scattering will be bare minimum. Okay, that is the definition of Fresnel scatterer. In such cases, what is going to happen? HH backscatter image will be brighter than VV backscatter image. Okay, but if here the material is dialectically inhomogeneous, and if the material is loose, unconsolidated material, geologically, for example, alluvium, isn't it? In case of alluvium, what is there? There are different kind of particles, different rock fragments, different kind of particles are there. Some particles are dry, some particles are wet. Okay, so wet particles means they are dielectrically strong. Okay, high dielectric property, whereas dry particles is low dielectric property. When this material has a low dielectric property, then what happens to this radar wave? You know, this radar wave can easily transmit through the material. Okay, but if this material has high dielectric property, that means if the material is wet, then what will happen? Then their electrical field will be generated, and then radar return will be very, very high. Okay, so return pulse will be very, very high. So in such cases, here the area will look bright. Now, in case of volume scattering, what happens? Your radar wave is going inside the volume of the material. It goes inside the volume of the material, then it interacts with different particles. There are multiple bounces are happening. After that, it is coming back. Okay, so that is why it is known as volume scattering. And volume scattering will be strong where the material is dialectrically inhomogeneous, dialectrically heterogeneous, where the materials are loose. See it? If the material is very hard, compact, then what will happen? The material will be low dielectric property. For example, in case of crystalline rocks, okay, all the minerals are interlocked. There is no the water in between, isn't it? So in such cases, what will happen? Dielectric property will be very, very poor. Then this radar wave, we can easily penetrate through it. Right? But if the minerals are hydrated minerals, then there will be a lot of water molecules. In such cases, it will come back. More this radar return will come back. Now you see, this is a very beautiful example where this polarization behavior of the electromagnetic radiation or the radar wave is very much exploited for different kind of applications. For example, for hydrological mapping, okay, or let us say drainage mapping, See, if you use HH polarization, this image, you see here the surface drainage are highlighted. They look bright, surface drainage. But in case of VV polarization, also surface drainage, but only those surface drainage where the topographic ruggedness is high, where topographic elevation difference is high. That means the major rivers, where the river banks are this substantial, okay, where the elevation of the river bank with respect to the background is good. So where the surface is rugged, okay, only those streams will be highlighted. But in case of HV, which is a cross polarized this your radar wave, so HV only those your streams, those are near surface, subsurface but very near to the surface, those your streams will be highlighted. So what you are getting, in this case you are getting the surface streams, in this case you are getting surface streams but the major surface streams, and in this case you are getting those streams, those are very near to the surface but a little below subsurface streams are getting much more highlighted. Does not mean that surface streams will not be seen there, it will be seen, but subsurface channels, those are not seen here at all, it will be detected here. So if you combine all this information, so three drainage map, if you combine, you will get much more, your drainage will be detected here. So your drainage map will be much more refined. Okay. Similarly, if you see in a land water boundary like Bay of Bengal, okay, so this is an example. See, in case of HH polarization, what it gives. In HH polarization, the land area is getting highlighted. Particularly the dielectric contrast, the material with the dielectric contrast will be discriminated easily. In case of VV polarization, vertical, here also this your land surface will be highlighted but not as much as HH. Here only those features, those are reflected through topographic ruggedness or topographic break, like beach ridge here you see, okay. This is Bay of Bengal, this is your is south of West Bengal, okay, and here it is the Odisha, this coast. These beach ridges are here very prominent, isn't it? Only the major your land surface features will be highlighted. Those are expressed through topographic breaks, through topographic ruggedness, so those features will be highlighted. Now in case of HV polarization, land water contrast will be highlighted, because you see in case of HV polarization, this your radar wave cannot go inside this volume of water, because water is fully saturated with the dielectric property, because its dielectric property, its dielectric constant is how much? Dielectric constant is above 80. Pure water has a dielectric constant of 87, isn't it? So this radar pulse cannot penetrate, cannot go inside water, it comes from the surface of the water. Whereas in case of land, what it does, wherever the material has this dielectric inhomogeneity, those materials, there will be good volume scattering. So those kind of features will be highlighted more. Okay. Now see how this radar image is very useful for geological applications. So if you use only optical image, you will get a beautiful color image, because you have a multispectral data, you have a red band, you have green band, you have blue band, you have near infrared band, you have SWIR band, isn't it? You have SWIR 1, SWIR 2. Okay. So from these different spectral bands, you can have a false color composite and a color image. But here, if you can fuse a radar image along with a color image from optical spectral bands, then the information content becomes, this is manifold. See here, we have the color information or spectral information from the optical spectral bands. Okay. So one FCC has been fused with a radar image, then what happens here? This geometry of this land surface, that means geomorphological features are getting highlighted, isn't it? You see here the structural hills is getting so much highlighted, and also you know radar wave is very sensitive to the surface roughness. That is why you see here their aeolian landforms, these are longitudinal dunes. So dunes are very prominent here, isn't it? Similarly, it can penetrate through ground. So subsurface features like buried paleo channels, you can see here, as also very prominent. You can identify from here. And see, this is an impact crater. The boundary of the impact crater is very sharp. Why? Because it is very sensitive to the surface geometry. Okay, like this, if radar image give you additional information along with the optical image. Okay, so those are the things we have started even decades back, but now there are advancements are happening. Not only this, but much more. But these are the certain advantages of the radar image along with the optical images. Now see, in case of this radar image, because it is very sensitive to surface roughness, so these different rock types, those have contrasting surface roughness, that can be highlighted, because if the surface is rough, backscattering will be more, then it will look brighter. If the surface is smooth, backscattering will be less, then what will happen? This area will look dark. For example, here in this case there are limestone, and you know this is the very cold climate. In this study area is from Canada, so very cold climatic region. So here limestone is very rough, isn't it? So very rough surface in limestone, and there is a sandstone here. So sandstone, you know, it is a medium grained sedimentary clastic rock, and here is shale and claystone. Then shale and claystone, they are very fine grained, so it is very smooth surface, whereas sandstone has this moderate roughness, shale is very smooth, and limestone is very rough. So that is why you see now their brightness is maximum in case of limestone because it is very rough, then followed by sandstone because it is moderately rough, and you see in case of shale or claystone it is very smooth, so it also appears dark. Okay, because without surface roughness, your radar pulse cannot scatter back. It can reflect, but reflect to other direction. It comes from this and going the other direction, but your satellite is orbiting like this, isn't it? So unless it scattered back, your antenna cannot receive, isn't it? That is, backscattering is important. So without surface roughness, backscattering will not be happening, isn't it? And surface roughness is a function of radar wavelength. Now this slide I discussed, I think, in the first day of my lecture. Here you see, in case of mineral exploration, if you use this radar image, the structural features can be highlighted and the structural features can be mapped very nicely. Particularly mineral deposits like hydrothermal mineral deposits, they are very much structurally controlled, isn't it? So in such cases, the structural features like your faults, like your lineaments, like fractures, like shear zones, so those features are very much highlighted. But if you fuse with optical multispectral image or with hyperspectral this image, then what will happen? Spectral information you can merge with the surface roughness information, and that is what it has happened here. The multispectral information is merged with the radar surface roughness information, and that makes this information content is manifold, isn't it? And mineral this targeting becomes much more easier than from the optical image alone or from the radar image alone. Now coming to this different radar imaging beam modes, like radar imaging satellite 1, this is the first radar remote sensing satellite from ISRO, okay, that was launched in 2008. No? So here there are different your beam modes are there, and essentially in case of radar imaging, you know there are 4 kind of beam modes in general. One is spotlight mode, another is your strip map mode, another is your scanner mode. Okay, so broadly 3 categories, but again in case of scanner mode, there are different kind of advancements are happening. Okay, from scanner to topsar. Now in case of NISR, from this scanner to sweepsar, so more improved scanner mode are available nowadays. Okay, now in case of strip map also, you can have a fine beam, you can have a standard beam, something like this. Now let us see in case of RISAT 1 this case. See, these are these imaging modes are available. FRS 1, okay, so fine resolution, these are strip map and spotlight mode, whereas FRS 1 and FRS 2 and MRS and CRS, they are under scanner mode. See, this is the swath size starting from 25 km for high spatial resolution to 223 km. For the coarser spatial resolution is 50 meter. Okay, Now the data is available in linear polarization, in a dual polarization, means two polarization. For example, HHBB or HHHB, something like this. And then you can have this quad pole or polarimetric SAR, okay, and also for interferometric SAR, okay. And interferometric SAR is much more available in the this new mission, that is RISAT 1A, okay. And RISAT 1, that are mostly it was focused mostly on the standard applications and some polarimetric and some radargrammetric and interferometric applications, but these are limited, okay. Now see an example of a RISAT 1 image. You see there are HH polarization and HB polarization. So two beam modes image we have used here. One is HH and one is HB. So HB is cross polarized image and HH is like polarized image. Now for this improving the spatial resolution, we have done some processing steps like adaptive filtering, multitemporal averaging, low pass filtering. Then we have subset this area. Now you see this is the area in HH polarization, same area, same time, two images are acquired, one in HH polarization and one is in HB polarization. But you see their appearance is not exactly the same, they are different. Why? Because in case of HH, here the surface scattering is dominant. In case of HB, here the volume scattering is dominant. Now let us see some this your test site, some parts. For example, in this particular area, you see, I am not going to geology at this moment, or geosciences or earth sciences at this moment. Just one interesting observation you can see. So here you see there is a lot of bright spots, but here bright spots are very less. Here there are some black spots. What are they? These bright spots are the overburden dumps. It is a mining area and settlement areas. And here these dark spots, these are the open cast mines, quarries. Okay, and this is river in both the cases. Now one interesting thing you can observe here. See what is this? There is some white across this feature across this river. This is the bridge. That bridge, it is very clearly visible in the HH image. But if you see in case of HB image, it is vanished. There is no bridge. Is it so? It is very much there. Then why it is happening? It is happening means in case of HB polarization, bridge does not facilitate this volume scattering. It gives only surface scattering. Because bridge behaves like a dihedral object. There will be double bonds, surface scattering. Okay, that is very, very strong in case of HH polarization, but in case of HB, it is almost negligible. That is why this bridge cannot see here, but bridge exists. It is there. Now coming to the geological features. See, this is HH image. Here in the mining area, there are quarries, there are the overburden dumps, coal dumps, all those features, geological features. Some this terrain, the ruggedness you can see because of some sandstone bands are there or ridges are there. So those kind of features you can see. But here you see this surface scattering is not very prominent here. Only you can see these quarries, dark spots are there, but one beautiful feature you see here, one linear feature. Here it is very, very faint, but here it is very clear. What is that? It is a subsurface fault, geological fault. Okay, it's weak plane. Under this surface it is there, but because the surface has been obliterated due to agricultural practices. These are all crop fields and this is the mining area. So the initial surface, when the fault was visible at the surface, that surface is no longer exist. Now it has been fully modified, but it is very much near surface. This feature exists, isn't it? So because this HB can penetrate, so this feature it can pick up, whereas in case of HH, it gets information only from the surface. So this fault is not visible here. So this is interesting observation you can see. This kind of observation you can make from this the HH and HB, how different they are scattering this your response is. Now coming to some polarimetric these properties. So you see in case of quad pole or polarimetric SAR, this your image. So this is the scattering matrix. We have HH component, we have HB, we have VH and VB. Okay, Now from that we can have a coherency matrix, we can generate a Pauli scattering vector, and we can generate a lexicographic scattering vector. So it is something like this. I am not going to the details. It is sum of this like polarization, difference of the like polarization, and it is the cross polarization. Here you see like polarization HH, okay, cross polarization and VV. Now from this coherency matrix or covariance matrix you can do many kinds of this decomposition. What is decomposition? From this full polarimetric wave you can decompose into different components. What are those components? These components which you can understand how much scattering is taking place from the surface, how much is scattering taking place from the subsurface. Okay, so surface scattering, volume scattering, and where there are double bound scattering is happening, or there are some because of the very your typical geometry of the features, okay, like helix kind of scattering happens. So those kind of things one can decompose. Essentially there are three components I am telling you. One is the surface scattering, one is the double bonds which happens from the dihedral objects like the buildings, like the bridges, like this, and the other one is the volume scattering due to the dialectically inhomogeneous materials, where the radar pulse goes inside the volume of the material, then there are multiple bounds is taking place inside, multiple scattering taking place inside, then it is coming back. When it come across, then one wet particles, okay, so dialectically a strong particle, then it will come back. Now this decomposition can be done by different ways. One can be coherent decomposition. It is particularly important for the pure targets where the scattering only very pure kind of scattering taking place, one kind of scattering, there is no mixture of scattering is happening, okay, for that kind of object it is very good. Incoherent decomposition, where the coherency matrix can be decomposed but the target is not very pure scatterer, it is a distributed scatterer where there is scattering is quite random, there is anisotropic behavior of the scattering is there. Anisotropic behavior means there is not just one dominant scattering but more than one scattering processes are happening, okay. So for such distributed targets this incoherent decomposition, and there are other decomposition like Pauli decomposition, eigenvector, eigenvalue based decomposition. I am not going to the details at this moment. So these are the possibilities before you. You can decompose a polarimetric SAR image, polarimetric SAR return signal into different components where you will be able to understand how much is the surface, this feature, how much is the scattering taking place from the surface, how much is taking place from the subsurface, and what is the feature geometry, what is the feature geophysical properties. As I started the discussion with the polarimetric SAR image, okay. So geophysical these factors, isn't it, and this your geometry, geophysical factors like dielectric properties, surface roughness, and the geometry of the object, shape, size of the object. So these are also important. So those kind of your phenomena, those kind of characteristics rather you can decompose. You will be able to understand the feature properties. Now you see just one example I am showing, not going to the details. Now the same polarimetric your image, that is a quad pole, which is a complete polarimetric image. From that you can decompose into entropy, you can decompose into anisotropy and alpha. So entropy means what is the degree of randomness. So scattering randomness, anisotropy, how much scattering process is happening, and alpha is the mean scattering angle, means how much, what is the dominant scattering process, that you can tell whether it is a surface scattering, single bounds, whether it is a double bound scattering, or it is a volume scattering, okay. So now if you combine these three together you would get a combined information of these different components, but you can separate out because you have assigned different colors, isn't it? You have assigned red for entropy, you have assigned blue for anisotropy, and you have assigned the alpha with this it is the green color, isn't it? So this is red, this is your this is anisotropy is green, sorry, and this alpha is blue. Now if we combine them together then it is appearing like this. Now see, this is how it has evolved. So like in the beginning, like in 1991 or so, you have only one polarization, only VV polarization, IIRS 1 data was available, European Space Agency IRS-1, that is the first satellite which was acquiring this C-band radar image. Although before that there were these radar data available by CSAT mission or by number of spacecraft, but this IRS-1 is the first your operational satellite which gives you this your C-band single polarization radar data. So it has both magnitude and this phase in case of C-band, but before that you had only magnitude, one polarization, only magnitude, followed by this one polarization, one phase, then two magnitude co-polarization phase, okay, then four magnitude, okay, then there is hybrid polarimetry, compact polarimetry, okay. So that means two linear polarization and their this phase difference, then finally all full polarimetry, okay, either 3x3 scattering matrix or 4x4 scattering matrix, where you have both magnitude, you have this phase for all these components, for HH, VV, HV, VH, all full polarimetry. So this is the evolution of this polarimetric SAR. I'm sorry I have not discussed in detail, and it may be very difficult for many of you. Those are very new to this subject, okay. But just you consider this. This is what are the possibilities, okay, for understanding this the concept or understanding the principle. It will take time, because the purpose of this today's lecture is, in 1 hour lecture, I have to address you many advancement in microwave SAR, so that you understand that what are the possibilities at this moment are there. So depending on your application, you can focus on a particular area like polarimetric SAR, or if you are interested in other kind of applications, you can focus on interferometric SAR or other kind of areas like radar grammetry or many more, okay. That is the purpose. For example, there may be this combination of these, okay, polarimetric and interferometry, okay. So now coming to this interferometric SAR, here what is that? It is synthetic aperture radar interferometry or interferometric SAR is basically, it is a particular technique. It is used for measuring the terrain topography, means good quality digital elevation model, then surface deformation. So interferometric SAR is essentially is used for getting a very good quality digital elevation model, but more importantly for getting spatially continuous land surface deformation in very high precision level. What is the precision? You know, centimeter to sub-centimeter level of precision, spatially continuous land surface deformation. For example, due to an earthquake, for example, due to volcanic eruption or volcanic upwarping, or because of a landslide, okay, or because this glacial movement. These movements you can measure. That is in a spatially continuous fashion and in precision of centimeter to sub-centimeter level. So that is the beauty of this technique. How it is done? You need to have two images, okay. So these two images you can acquire at the same time. Then from these two images you can generate a digital elevation model, or you can acquire these two images some time gap. For example, if you want to map or measure the land surface deformation due to an earthquake, then you need to have one image before the earthquake, another image after the earthquake. Now, taking these two images, one before earthquake, one after the earthquake, these two images you have the phase information. Now, you calculate what is the phase difference by interferometric SAR processing. You calculate the phase difference, and in this phase difference, this pixel which is moved, that movement of the pixel can be detected. And this movement of the pixels in centimeter to sub-centimeter level of precision you can detect, and you can measure, and you can map. So that is the beauty of this technique, where there are no other technique exist, no remote sensing or geodetic technique exists other than interferometric SAR, where you can get spatially continuous land surface deformation at a precision of centimeter to sub-centimeter level. You can get centimeter or sub-centimeter level precision in case of many terrestrial geodetic techniques like terrestrial leveling. You can get it in case of very your geodetic GPS or geodetic GNSS observation, that is permanent GPS or core station, or even campaign mode as well. You can do that from GPS point, very high precision your deformation, but it is a point-based information, only for a point. But in this case, you have the spatially continuous information. Like this, you see the application. Due to an earthquake, how the displacement happened, that can be mapped. And these are the cycles, what you see, rings, color rings. This color rings represents the phase cycles, phase difference of the two images, one before, one after. Okay, and each color rings represent lambda by 2 displacement, lambda by 2 along the direction of radar beam. Okay, so here you can see that here the color rings are oriented towards this, and here the color rings are oriented towards this. So displacement is like this, isn't it? Then what kind of fault it is? It's a strike slip fault. So this strike slip faulting is responsible for this earthquake. This is the Landers earthquake, and in fact this is the first interferometric SAR image which showed the land surface deformation for the first time. Okay, and this earthquake occurred in 1992, and this paper was published in 1993 on Nature. Now you see, this is another example at the mining area. We processed this data of this Dhanbad Jheria coalfield, and we processed in the late 90s, in the early 2000, and from that we get the phase difference here, and this is the correlation coefficient, and from this phase difference we can we generated one very high quality DM, and many more applications we did from the DM as well as from the correlation coefficient. But most important applications of differential interferometric SAR, or you say interferometric SAR, okay, INSAR and T-INSAR, is land surface displacement or land surface deformation, like earthquake, like landslide, like volcano, like glacier, and land subsidence. And why land subsidence? How land subsidence happens? For example, in case of mining, when you mine out this material underneath, like in case of coal mines, if you have a underground coal mines, you are mining out, extracting the coal from underneath, then what will happen? There will be void space. Then this overlying this your this load, that is the overlying this your rock layers, that will be subsiding, isn't it? And when it will be subsiding, and a shag will develop, and finally there will be this your roof collapse will happen, and there may be this a lot of damage can also happen, isn't it? Similarly, due to groundwater pumping, this your groundwater horizon aquifer can be empty, and this your land surface can be subsiding. Okay, and all of you know that earthquake causes lot of subsidence, landslide causes lot of movements of the material, then volcano also, and glacier also, because glacier moves. But you know, glacier is a solid mass, so this displacement of the glacier can be very nicely mapped by this technique. But the displacement of a flow in a river, the water flow cannot be mapped, because there is a problem of correlation of the pixel. Now see, here it is one of the very interesting, this example of interferometric SAR is the first basically application of high quality DM generated by this INSAR technique, is this SRTM mission. Okay, although this INSAR based DM was generated even in the 1980s. As I remember, it is in 1988 this was generated by the JPL group. Okay, Goldstein and Jipker, perhaps they processed INSAR data from spacecraft and generated a DM. And later on in the 90s, many people used this IIRS-1, IIRS-2 data. Okay, and from that IIRS-1 and IIRS-2, they have generated the DM from the 10 pair. Now, but that is only for selective areas. Okay, but in case of shuttle radar topography mission SRTM, that is a spacecraft, it acquired data for the entire globe, except the polar region, around 60 degree on North Pole and South Pole. Is here it is exactly written 58 degree north and 56 degree south, up to that. Now you see this, in the same spacecraft there are two antennas. Here is the transmitting antenna transmitting this green, that is the transmitting wave, and here is one receiving antenna, here there is another receiving antenna. So two pulses are received at a distance of 60 meters. Okay, so from these return pulses, okay, two radar image can be obtained, and from these two radar image you can have interferometric this processing, you can have the phase difference, and from this phase difference you can get the height of the object. height of the surface with respect to the geodetic, the ellipsoidal surface. Okay. So now coming to other applications, like similar kind of application was done by this TerraSat Tandem X, by this German satellites, TerraSat X and Tandem X. There are two satellites. One was launched 2007, another 2010. Now from these two satellites, we have at the same time two images, and from these two images the DM can be generated. And the DM is a very good quality, and its vertical precision is close to 1 meter. 1 meter to 2 meters vertical precision is very high quality, because it is a DM, it is not displacement. And for land surface deformation, it is centimeter to sub-centimeter. But for digital elevation model, it is not millimeter, centimeter, but it is in meters precision. Similarly, we did it for this Jharia coalfield, as I already explained to you. And you see here, this is the Jharia coalfield is one among the 54 plus Gondwana coalfields in India. Okay, so here this problem of environmental impacts, the problem of land subsidence is not only in Jharia coalfield, but many other coalfields are similar problems are there. But although the problems are more severe in case of this Jharia coalfield, because it is very old coalfield, and there are a lot of this mining has happened, and without much this care about the environmental impacts, without much your measures to arrest this thing, land subsidence, to arrest fire, but only mining, because it is a pre-nationalization period. So this is this kind of mining has happened without taking care about your damages it can happen. Okay. Now we see from this interprogram, you can have the digital elevation model, you can have the correlation coefficient image, and from that you can get different kind of this mining indicators or environmental impact indicators, like coal dump, like overburden dumps, like your open cast mines, then closed or abandoned mines, like this you can have. Now from this difference in interferometry, where the movement also you can detect and measure. Now we have used C band and L band, and you see this is the area which is subsiding in this coalfield. It's much more large area here, because here the C band is the shorter wavelength, whereas L band, because it is longer wavelength, it can give you this area which is subsiding at a very faster rate. And in case of C band, because wavelength is shorter, it is only 5.6 centimeter, whereas L band has wavelength of 23 centimeter. So that is why here the fast subsiding areas are detected, and here the slow subsiding areas are detected. And these subsiding areas, what we get from the interferometric SAR, you can compare with the actually surveyed subsiding areas, and you can see there is good agreement. In fact, from interferometric SAR technique, you are getting some more areas of undergoing subsidence, some additional areas undergoing subsidence that you can identify here, because surveyed these areas are only this in and around the mining area, where they are going to do the present day mining. But outside the present day mining area, the surveying is not happening. But there are some old abandoned underground mines where subsidence are happening till now, and those areas we have detected here from interferometric SAR technique. Similarly, there are other very good application is in case of coastal dynamics, coastal transgression, coastal erosion. So here you can use the interferometric SAR coherence image, and the land water boundary you can have. So land water boundary you can map for different periods, and from these different periods of land water boundary you can see how this coastline or shoreline is changing with time, whether the shoreline is extending towards the sea or the shoreline is going inside the land. That means whether the area is eroding or whether the area is depositing. So that kind of study we have conducted here, and you see here the green areas where the shoreline is extending towards the sea, so depositing areas, and red areas where the coastal area is eroding. Okay, so this is very interesting study. One can do with the INSAR coherence only. Here you are not measuring the displacement or subsidence or any kind of land surface deformation, but you are measuring what? You are measuring how the shoreline is changing. land water boundary is changing. Okay. Now you can have application in case of this gully erosion, like in case of ravines, like in Chambal, Jamuna ravines. There are wide ravine belt on either side of the rivers. This is Chambal river, and this is the agricultural fields has been degraded by the gullies network, which is known as the ravines, isn't it? So here we have used this synthetic aperture radar image, that is the amplitude image, as well as interferometric SAR processing we did, and based on that we have studied how much this area is eroding, okay, how much the area is getting damaged with time, and what is the potential of damage, potential of erosion by ravine your migration, and what is the depth of the ravine, okay, what is the density of the ravine, what is the ravine surface cover, that we have studied. Okay, first is from the textural information, second is from the phase information. We get the interferometric surface, from that we get the DM, and from the DM we are getting this different ravine depth, shallow ravines, moderately deep, and deep ravines. Then the surface cover from the correlation coefficient, whether it is covered by forest, whether it is covered by agricultural land, or it is a barren land. Okay, so those kind of information you can extract from here. Now again, coming to this land surface deformation like earthquake study. So this slide we have already explained to you. This is a landers earthquake and how the displacement is happening, that you can understand now. So this is moving towards this, this has moved towards this, and here is the fault, and this fault is a strike slip fault. Similarly, in case of Nepal earthquake, you see this that happened in 2015, isn't it? See, this area uplifted in and around Kathmandu is uplifted suddenly with the earthquake. How much you know? 1.7 meter. It is uplifted. It was uplifted 1.7 meter along the radar beam direction. Definitely 1.7 meter. It has gone up, and on the northern side, it went down. How much? 60 centimeter. It went down. Subsidence, and in between, there may be this geological structure like MCT. Okay, this is the situation of the main shock. Similarly, due to the major aftershock that happened, that occurred in Kodari area, this aftershock was 7.3 magnitude, whereas the main shock was 7.8 magnitude. Nepal earthquake, main shock was 7.8 magnitude, and the major aftershock was 7.3 magnitude. Okay, this occurred in 12 May 2015, and you see this is the area affected. This area was, your land surface was displaced. Here uplift took place. How much you know? 65 centimeter uplift took place, and here subsidence took place around 35 centimeter. Now see, in case of volcano, you can see this due to the volcanic this upwarping, or after volcanic eruption there can be subsidence. Okay, so we can study, we can detect, we can measure how much this subsidence or upwarping is taking place. These are the volcanic cones where the upwarping is taking place. Some areas there are subsidence also taking place. Here, for example, after the eruption in 1998, there are subsidence is taking place. But these are the volcanic cones. Here there are upwarping is taking place, and from the rate of upwarping, one can model and one can predict to a great extent. One can say that when this volcanic eruption is going to happen based on this modeling approach. It will not be very this accurate, but it will be very close to your actual eruption this time. Okay, so the rate of upwarping one can get from here. Similarly, in a landslide, you can get how the landslide moved in different parts of the landslide. Okay, at different time interval. That you see this, we have done this landslide movements we have mapped. Okay, in the Garhwal Himalaya. Okay, these are the patches where the landslide movement is very, very prominent. So this is the area is very near to the Pipalkati on this area. This basically here Gonatal area and on the Biraita Ganga, the river. Okay. Now see, in and around this your Terry dam or Terry reservoir. Okay, on the rim area there are a lot of slow landslides are taking place. Slow landslide movements are taking place. Okay, this is due to rainfall, but most importantly because of the reservoir water impoundment. Okay, So this low deformation also can be mapped, and we did this study. But this is your previous study, we did it, but we are doing with advanced interferometric SAR technique, so that we can have much more precise information about the deformation. Now in land subsidence, you see the impacts of land subsidence. This is the roof collapse, okay, due to this your underground mining. Basically this is an old gallery. There was the subsurface fire was there in the coal field, in Geria coal field, and the roof collapse took place, and you can see how that land is subsiding because of underground fire. These are other areas. Now see, in different other cases, you see there are the wide open cracks. This is a slanted building, isn't it? You see how the land subsided, isn't it? There are the cracks here. The land is subsided, and you see the building appears to be uplifted. Here you see the oil casing, it is gone up. Actually not. Land surface has gone down. Okay. Now these are the different examples. You can see that, for example, we have studied in case of Indonesia. Okay, in Indonesia in Bandung area, you see different patches are subsiding. Even one patch is very close to the airport, one patch in the city center. Why this subsidence is taking place? Because the groundwater pumping is very high rate is happening. People are pumping out, people are extracting groundwater at an exorbitant rate. Groundwater recharge is not taking place at that rate. Much less rate recharge is taking place, but they are extracting much higher rate. Then what will happen? Aquifer becomes empty, and then aquifer compaction is taking place. And because aquifer compaction is taking place, overlying this your load, it is going down, and then land surface is subsiding. Okay. Similarly, we have studied in many of the Indian your sites, like we have studied in Delhi, in and around Delhi. We have studied in and around Mohali, Chandigarh, and many other areas in Kolkata. Okay, so we have seen that in many areas there are groundwater. This level decline is very, very strong. These are the extent of groundwater level decline. It means groundwater depletion. Okay, so because of this groundwater depletion or groundwater level decline, what will happen? Aquifer becomes empty, and the aquifer will get compacted, and the land surface will be subsiding. That is what is happened in case of Mohali, in case of Kharar, Chandigarh also, but Chandigarh subsidence is much, much less. This you see very precisely, we have mapped it in Mohali area, and this is the advanced, this your from advanced DNSR, this is the time series deformation history, time series subsidence history. Okay, how the subsidence is taking place over the years. And you see here almost how much from 17 to this year 18, there is a subsidence of how much? It is almost 160, means around 8 centimeter per year. So we have measured there is a maximum subsidence rates even up to 10 to 12 centimeter per year. Okay, and if the subsidence rate is so high, there will be a lot of damages will happen on the your buildings, on the houses, on the surface infrastructures. See it. Now in the present slide, this micro remote sensing can be used for planetary geological study, and here we study mostly using this Chandrayaan-1 mini SAR and Chandrayaan-2 dual frequency SAR. Okay, so here you see in case of mini SAR, this is the North Pole and South Pole. We have studied number of test sites. Okay, and now the purpose is to understand what is the scattering processes, what is the scattering happening inside the crater, at the center of the crater, on the background where the regolith occurs. And we have studied how much surface scattering is taking place, how much volume scattering is taking place, or the surface is very rugged so that it is radar pulse is coming, it is hitting, it is reflecting, again hitting, and it is coming back. That is double bounce. So how much is surface scattering, how much is double bounce, how much is volume scattering? That gives us this information about the your morphology of the lunar surface, about the lunar surface material properties. Okay, whether these are loose materials or not, whether there is water ice is there or not. So those kind of information we can have. If there is loose materials, then there will be a lot of volume scattering. If there are these big rock chunks or there are rugged areas, there will be a lot of double bounce scattering. So this is the purpose, to understand the lunar surface. Okay, to understand the planetary surface, their morphology, their geometry, okay, their ruggedness and the material property. This is the purpose. Now here we have studied some advanced your indices like circular polarization ratio, degree of polarization. Then we have decomposed this polarimetric SAR. This is hybrid polarimetric SAR or compact polarimetric SAR. We have decomposed, and by decomposition we can see what is the scattering process, what is the degree of polarization, and based on that we can infer that in the deep crater, that is permanently shadowed crater, if you see, there are a lot of diffuse scattering is taking place where the CPR value is high, okay, and based on the scattering processes we can infer that there is a possibility of having water ice, okay. So availability of water was confirmed, one from microwave SAR image, another from hyperspectral sensors, okay, MCube in Chandrayaan 1 and IIRS from Chandrayaan 2. So with this I'll stop today's